Well, by now, you're very well aware of how strong the magnetic field is at some distance from a long straight wire. You should be able to derive using either the law of Biot-Savart or Amperes Law. If we have a wire carrying a current I, then the magnetic field at point P, which is located at a distance of r from the wire, is equal to 2 times 10 to the negative 7th times I divided by r. Or if you wanted its original form, mu naught over 4 pi. Mu naught over 2 pi times I over r. Well, what about this? Is there any magnetic field inside of the wire? So if we take a magnified view of this wire, we know for sure there's magnetic field lines that are pointing out of the page at points above the wire and into the page at points below the wire due to the fact that the current was flowing to the right. I would have said just the opposite of that if current was flowing to the left. But what about at points inside the wire? Turns out there is some magnetic field at that point P as well. So to find that, we could use Amperes Law. Remember, Amperes Law tells us that the total loop integral product of B dot ds is equal to mu naught times the amount of current enclosed by the Amperian loop. So I'm going to draw an Amperian loop, and I'm going to make my Amperian loop so that its edge coincides with the location of the point P that I'm interested in. So I'll make an Amperian loop in the form of a circle that looks something like that. So I'm going to say the radius of my wire is capital R, and the radius of my Amperian loop is lowercase r. So if this has a uniform current density, remember J is the symbol for current density. If it's uniform, then the amount of current that passes through my Amperian loop is only a fraction of the total current, right? Some of the current passes through here, but some of the current skirts past that Amperian loop. So we could change Amperes Law to a more general form and say the integral of B dot ds equals mu naught, and to get the amount of current enclosed, we could integrate, and remember that I is equal to the integral of j dA. So there we have it. Okay, now let's look at the Amperian loop that we chose. It was a pretty good choice. We can assume that any magnetic field that does exist inside of the wire is going to point tangent to my Amperian loop at all points, so we can get rid of the dot product. Ignore that. And I think the magnetic field at this point is just as strong as it is here or here or here. So the B comes out of the integral sign, and we have B times the integral of ds is equal to mu naught. Now if the current density is uniform, then I can pull it out of the integral sign. So we get mu naught times j times the integral of dA. So we get B times, now this just means find the total length of your Amperian loop. So this is B times 2 pi. Now you know I'm going to say r, but which r? Lowercase r, right? That describes the circumference of my Amperian loop. Capital R is the radius of the wire. So B times 2 pi little r is equal to mu naught times j. Now the integral of dA just means the total area of my Amperian loop. So this gives us pi times little r squared. So we can cancel out the pi. We can even cancel out one of the r's, and we get B is equal to mu naught times j, the current density, divided by 2. So we've got the mu naught, the j, divided by 2, and then we're left with r. So if we were to make a graph of the magnetic field as we work our way out from the center of the wire, then it looks like from the center of the wire all the way up to the edge of the wire that B is proportional to r to the first power, which just means the magnetic field grows linearly until we get to the edge. Now, once we get to the edge of the wire, any Amperian loop that's drawn to find the magnetic field at points outside of the wire, there is no additional current enclosed by my Amperian loop by making my Amperian loop wider. Once I've made it up to the edge, the amount of current enclosed is all the current. So in other words, the current enclosed by Amperian loop number 2 is the exact same amount of current enclosed by Amperian loop number 3, because there's no additional current at points outside the wire. Both Amperian loop 2 and Amperian loop 3 both enclose the total current of the wire. So we know that the magnetic field at points outside of the wire go as a proportionality. B is proportional to 1 over r. So from the middle of the wire outward along the radial axis, the magnetic field increases, reaches its maximum value right at the edge of the wire, and then decreases from there onward. And this graph says that the increase inside the wire is linear, and then outside of the wire goes as 1 over r. Now, what if the current density is non-uniform? In that case, we could make up a value if we wanted to, and just say hypothetically, what if the current density gets greater and greater as you work your way out from the center of the wire? What if there's only a little bit of current carriers near the interior, but a lot of current out near the exterior? There's something known as the skin effect, and some wires indeed do behave in that way. Most of the current is conducted on their surface and not on their interior. And maybe we can describe that by saying J is equal to alpha times r. So Amperes law says the integral of B dot ds is equal to mu naught times I enclosed, but then again, I enclosed can often be replaced with the integral of J dA. Now we'll always choose an Amperian loop such that the magnetic field can be taken out of the integral. And so the left side of the equation will always kind of work out in the same way. It's just going to be B multiplied by whatever the length of your Amperian loop is. If my Amperian loop is a circle, then this becomes B times 2 pi r. On the right side of the equation, if J is uniform, I can pull it out of the integral sign. But in this case, we made up a hypothetical scenario where J increases, the larger r happens to be. So I just make a substitution, and I replace J with alpha r. And then what can I substitute for dA? So if this is a picture of the wire, then I need to imagine how much current is enclosed by that Amperian loop. So I imagine, first of all, how much is enclosed within that circle. And then on top of that circle, I add a little more area, like this. I add a little more area. So each of these rings represents a fraction of the total surface area of my Amperian loop. And each one of those rings has an area of 2 pi r dr. So we substitute alpha r for J and 2 pi r dr for dA. The 2 pi cancels out, and we get B is equal to mu naught over r, got the mu naught and the r, times the integral of alpha r squared dr. And if I want to figure out how much current is enclosed by this Amperian loop, then I need to integrate from 0 up to lowercase r. So the integral of alpha r squared is 1/3 alpha r cubed, and when I evaluate that from 0 to r, I don't really have to bother with the lower limit. So we get b is equal to mu naught over r times 1/3 alpha r cubed. That r cancels with one of those to make this r to the second, and we get b equals mu naught alpha over 3 times r squared.